Hey everyone, in this video walkthrough, I'll be going over parts B through F on the CS61B Spring 2022 final problem number 5. So let's get started. Okay, the first part B, states which of the following are true. Assume that all edge weights are non-negative. And in the first one, we have a graph with vertices V1 through Vn with one edge from V1 to each of the other vertices and with no other edges. Do Prim's algorithm and Dijkstra's algorithm produce the same tree when started from V1? All right, so imagine I have some graph where we have V1, then we have V2, V3, and then maybe some other edges and vertices, and then we have Vn. And the question is saying, hey, are the Prim's MST and the Dijkstra's shortest paths tree when starting from V1 the same? So the answer here is yes, they are indeed the same. The reasoning is when you're kind of considering Prims and Dijkstra's, they both find a spanning tree for the given graph. Right? That's what Prim's and Dijkstra's algorithm do, is that they say, hey, Prim's algorithm finds a spanning tree that happens to be the minimum spanning tree. Dijkstra's algorithm finds a spanning tree that happens to be the shortest paths tree, right? So if it's the case in our graph over here that the graph is a tree, right? Kind of notice that this graph is a tree because there's v minus 1 edges and all the vertices are connected. So you can kind of think about this graph as a tree, and it should look like a tree, right? It kind of looks like the classic tree that we talked about in our tree unit. So if this graph is a tree, then what you can kind of deduce is there's only one spanning tree, right? That's just itself. So if there's only one spanning tree for any given graph, then Prim's and Dijkstra's algorithm are going to find that same spanning tree, right? So they will produce the same tree, and that's why the first one is true. All right, so looking at the next one here, this next one we have some star vertex when we do A star search. Let's just call that A, and then we have some goal vertex that's called that G. So it says here, the time required to perform A star search on any connected graph with V vertices and E edges is omega of V. So this is actually not necessarily true. If it's the case that when I'm running A star, the goal vertex is very close to the start, let's say it's like a neighbor of the start, then we don't really have to consider the rest of the graph, right? There's no point maybe considering the rest of the graph. So in essence, all I'm really doing when I'm running A star in this example is I start at A, then I go to G, I see my goal vertex is G, I terminate my search. So you could think about in the best case, A star search has kind of like a constant bound. So this is not true, but it would be true if this was omega of 1, right? So looking at the next one here, the next one states in a connected graph with v vertices and v squared over 3 edges, Kruskal's algorithm will output v minus 1 edges. So this one is in addition true. And if you don't even think about it too hard, if you just kind of notice that the graph is connected with v vertices, then Kruskal's algorithm will always find a minimum spanning tree of any connected graph. So any minimum spanning tree will always have v minus 1 edges. That's just a property of a spanning tree. So you don't even have to like think about these weird number of the edges. All right. So this part here is dropped, and I think there's an explanation on Piazza about it, so we'll skip it for now. Yeah, we'll skip this part. Okay, the next one states, Dijkstra's algorithm always removes nodes from fringe in order of their distance from the starting node. So this one is also true, and this is just kind of like the intuition and actually implementation of Dijkstra's is you want to visit vertices in order of the distance from the starting node to ensure that we don't visit a vertex unless we found the shortest path to get to that vertex, right? And if you guys want a little more explanation, I recommend watching the content review video that I think is linked in the exam prep playlist during our shortest paths discussion. It talks a little bit about the Dijkstra's intuition there. So, moving on to part C. Part C states, which of the following are true about a game tree in which the top node represents a position where the maximizing players to play and the alpha beta search is used, and we evaluate child nodes from left to right. So the first one states, if a winning position for the maximizing player is found during the search, all other moves for that position are pruned and the search terminates. So this one isn't true. One way of kind of thinking about it is, let's say we have some maximizing node, and we have two minimizing nodes here, and then maybe we have a maximizing node down here, right? Suppose that this maximizing player finds a winning move, which we'll kind of denote as positive infinity, right? If this maximizing player sees a positive infinity, that doesn't mean that this minimizer above it is going to choose that route, right? Imagine that this maximizer node had like two values, like 2 and 4, then this minimizer will probably say, hey, I'd rather go to the right than go to the left. So the search wouldn't really terminate. All right, so the first one, yeah, is false. Moving on to the second one. Second one states, assume that winning positions and only those result in static evaluations with the maximum or minimum value. If the value at the top node is one of these two values, one side must have a forced win. So this one is actually true. And I think the intuition for that is if you're kind of looking at a game tree, let's say I have some sort of game tree here. And let's say that at the top, we have a value of positive infinity. So what this is saying is that the maximizer is guaranteed to win, right? If the value of the top node is positive infinity, that means that the maximizer has found a path in this game tree that leads it to a state in which it can win, and the minimizer can do nothing about it, right? And in a similar fashion, if there's kind of a negative infinity here, the maximizer is guaranteed to lose, right? And the intuition is that this represents the best thing the maximizer can do. If that's negative infinity, that means that no matter what the maximizer will do, it'll always end up in a state where the minimizer wins, right? Okay, so moving on to the next part, the value computed for a node in the tree will always be between the alpha and beta values for that node inclusive. So this is actually false. So the intuition here is a very challenging subpart, I'd say. So suppose that you have some sort of node, right? And any type of node, you're going to keep track of the alpha and beta values for that node, right? So initially, you could say the alpha starts off as a negative infinity, beta starts off as infinity. And as you kind of search, maybe as you go down some tree, maybe these values get updated, right? So let's just maybe think of an example. Let's say, hey, let's say that this is 10. So then alpha will get updated to 10. Or yeah, let's say alpha gets updated to 10 as we kind of like start in this node, then we go to the left, then alpha will get updated to 10. And then let's say, hey, let's go down to this node here. And let's say that on this side, we had a 30. Then this beta value will get updated to 30 because 30 is smaller than infinity. So now let's say that we get to this maximizing node down here, right? And let's say that this maximizing node, just for simplicity, let's just say it has one child, okay? So what I want you guys to do here, maybe a little challenge, is try to think of an example for a value here that's not between alpha or beta, and it's kind of a contradiction to this claim, okay? So yeah, maybe give it a second thought. All right, so let's maybe try some ideas here. So what if I make this value like 40, right? 40 is currently outside of this range. Does anyone see a concern with this? So the reasoning is like, if I make this value of 40, what's going to happen is that what we're going to do is we're going to say, hey, the value for this node is now going to be 40, right? And maybe like we update alpha to be really, really big. So maybe like it's the case that we decide to set alpha equal to 40, just depending on how the algorithm is implemented. Because usually in like the alpha beta pruning algorithm, what we do is I say, hey, I have some sort of response to my like mini max call. And then I set alpha equal to the maximum of alpha and my response, right? This is usually what we do in minimax, right? So if I see a 40 comes up here, let's say 40 is the value of that response, then alpha will also get set to 40, right? So technically this value that we return from this maximizer node is still like in the range of alpha to beta that you could say. So one clear way in which it's not going to be in the range of alpha beta is instead of having a really big value here, what if we have a really small value here? Let's say we have the value of -10. So if we have the value of -10, then notice what's going to happen is that this node's value is also going to be -10 because that's the best it could do, right? So if this node's value is -10, notice the -10 isn't between 10 and 30. So that's a good counterexample for this point here. So if you're at a maximizing node, the gist is like, if you have really, really poor options from a maximizing node, it actually might be outside of this range, right? Nice. Okay, so the next one says, if you minimax search processed m nodes in the game tree, use space proportional to m to represent the tree. So this one is actually not true as well. And the intuition for this one is that when you have some sort of game tree, we can just kind of keep this one here. Let's say that we have like a really big game tree, okay? Okay, when we have a really big game tree, you can think that each one of these nodes just kind of represents a recursive call, right? So each one of these is just a recursive call. So when we do recursion, we only need to keep track of our parents for when I terminate the recursive call, right? So the total amount of space I need to keep is just kind of the height of the tree, right? So we're not actually creating this tree in code. All that we're really doing is we issue a bunch of recursive calls using the minimax algorithm, and these recursive calls intuitively form a tree, but we're not actually creating this tree in code, right? It's just the fact that the minimax recursive calls kind of look like this tree when you draw them out, right? But the only space that we actually use is the space to keep this recursive stack, right? And the amount of this recursive stack is fewer than m nodes, right? If this is total of m nodes, you can kind of think that maybe this recursive stack is somewhere on the order of log of m, right? That's maybe a fair claim to make. So the last one here is that the value at a node of a game tree appears somewhere among its descendants. So this one is actually true. So the reason for this one is that if you have some sort of value at a node in the game tree, let's say like we have some value 10. So what the value 10 is saying is that from this node, there exists a path somewhere down the game tree that lands us into a spot in the game with value 10, right? So this 10 has to come from somewhere, more specifically, kind of gets pushed up a path to the current node. So you can see that if this node's value is 10, it must be one of the descendants must be 10 in order for the 10 to get up there. So that's why this last one is true. All right, let's move on to part D. So for part D, we have a min heap stored in an array with n items, and we're trying to find the largest item. So this one is actually true. Finding the largest item takes omega of n time. So the reasoning here is if you're trying to find the largest item in a min heap, so the largest item must be a leaf node, right? So the intuition is if you have some sort of heap, my claim is that the largest item must be one of these three elements, right? Must be one of the leaf nodes, right? Suppose, like, for sake of contradiction, that the largest item was this green element here. Well, we know that, hey, like, maybe let's assume that elements are distinct. We don't even have to make that assumption. But in this case, like, if the elements are distinct, then this item could not possibly be the largest, right? And even if the elements aren't distinct, like let's say this is a 10, then we only still really need to consider these leaf nodes, right? So if the elements weren't distinct, let's say this one has a value of 10, then we still really only need to consider the leaf nodes when we're trying to find the maximum, right? Okay, so the next question is, like, we know that the maximum must be one of the leaf nodes because any leaf node, you could think about it, is bigger or equal to all of its parents, right? That's the intuition once more. So how many leaf nodes are there in a heap, right? So if you have some sort of heap, in this case, you kind of see there's like roughly n over 2 leaf nodes, right? So it turns out this is generally the case, right? If you have any type of heap, the amount of leaf nodes you have is on the order of n over 2, right? It may not be exactly n over 2, just depending on like how the tree looks. Like if I kind of look in this example here, it is actually n over 2. Maybe I look at this example here. Turns out it's still n over 2. But yeah, the gist is like the number of leaf nodes is basically n over 2. So we have to look at all of the leaf nodes. So finding the largest element, we know it must be a leaf node, but we don't know which one. So we'll have to look at all of the leaf nodes. So we got to consider every one. And since there's roughly n over 2 leaf nodes, looking at each leaf node takes us n time, right? So that's why this is a valid lower bound on the time of finding the largest element. So in this one here, finding the kth smallest element requires big O of 2 to the k time. So this one is also true. The reason for that is if you have some sort of heap, and I'm trying to say, hey, I'm trying to find like the third smallest element, we only need to consider the first k levels. Okay, the intuition for why this is the case is that if the third smallest element is somewhere in this heap, it either is going to be in this level, or this level. So let's say, hey, Soham, why can't this third smallest element live right here? Well, we know that these three elements are smaller than this element here, so it can't be the third smallest. It must be like the fourth smallest, right? So if you're trying to find like the third smallest element, we only need to consider the first k levels, and the number of nodes in the first k levels is big O of 2 to the k, right? Or is 2 to the k. So if you're kind of considering like these three levels, the number of nodes in these levels is like around 2 to the k, right? So this is true. There's a naive algorithm to find the kth smallest element is just to consider every element in the first k levels, and that takes big O of 2 to the k time, right? So let's consider these next two parts here. So to delete an element at position k in the array, one can simply replace it with the last element in the heap, then heapify down, and then decrement the size of the heap by 1. So let's see, like, maybe if that's going to work or not. The proposition is that if we have, okay, let's say that we want to replace this element. So what we're going to do is put this element in here and then heapify it down, right? So the other option, actually, let's just tackle both parts at once, is that instead of heapifying it down, we might have to heapify it up, right? So the actual answer is both of these aren't correct. The reason is, like, we don't really know whether we need to heapify it up or down, right? So depending on the heap, we may need to heapify it up or we may need to heapify it down. So let me kind of give you like 2 examples. I'll try to create them on the fly. So let's say that we have the elements like 1, let's say 4, 10, 3, and let's say that this is 7 and 20. So if I put this 20 here, then obviously we'll have to like move it down, right? So if it's the case that the heap kind of looks something like, let's say look a little differently. Let's say we had like a 1, then like a 10, then like 11, let's say 12, 13. And let's just kind of ignore these elements here. And then on this side, let's say that we had like a 2, 3, and then the 4. Right, so let's say like this is the last element, and let's say that we were moving this element here. Right, so I take this element 4, I could put it in this spot, and then what we'll notice is I will have to like swap it upward, right? We'll have to heapify up. So it really just depends based on the current state of the heap, whether we have to go up or down on that given element, right? So we can't generalize to always doing down or always doing up. Okay, so this next one is actually true. The second smallest element in a heap cannot be at the bottom unless n is less than or equal to 3. So yeah, that is true. But think about it. Suppose that you have a heap with more than 3 elements. Let's just think of like the smallest counterexample, which is 4. And let's say the second smallest element was here. So if you say, hey, the second smallest element lives right here, well, that's not true because these 2 elements are smaller, right? Because this element is smaller than its child, and this element is also smaller than its child. So at best, this one could be the third smallest, right? Not the second. Nice. Okay, so last one is adding n items to initially empty min heap in strictly decreasing order requires n log n time in the best case. And this is also true. So the intuition here is if I keep adding items in strictly decreasing order, every time we insert an item, it's going to swap all the way to the top, right? Shoot, let me try to improve my lighting. That's good. So if an element always swaps all the way to the top, you can kind of think about the total amount of work that we're doing is going to be like log of 1, maybe log of 2, like log of 3, plus log of n. And if you guys kind of recall the sum, this is on the order of n log n. And this should be a sum that we've maybe seen like in heap sort, right? If we keep doing removals in heap sort, we kind of get this sum just in reverse order. So yeah, it's going to be n log n because every time we insert an element, it has to go all the way to the top. So log n time, and then we do n of them, so n log n. Okay, let me change that angle a bit. All right, so let's move on to the next part. Oh, nice, E. So a hash table uses external training, but instead of using a linked list, each bucket stores its items in a red-black tree. If there are n keys and n buckets, by what factor can the maximum search time required for a bad hashing function exceed that for a perfect hashing function, right? So if you think about a perfect hashing function, you can kind of think that every element goes to a new bucket. Or you can maybe just quickly say, hey, it's going to be constant time if the hashing function is perfect. On the other hand, if we have like a bad hashing function, you can kind of think about like every element goes to the same bucket. So the time then is how long it takes to search through a red-black tree with n elements. which is actually n. So if you have a red black tree with n elements, it's going to take us log n time. So the comparison is we have constant here in log n, so the factor that it's better is going to be log n. Or the factor that in which it exceeds the runtime is log n. Okay, let me improve my lighting. Give me a sec. Okay, so I think I improved the lighting marginally, but let's finish this recording. So part F states which of the following statements are true. Assume the tries are represented as presented in lecture. In particular, each string ends in a special character. The lecture used this kind of square symbol that is not used elsewhere. So what that is kind of saying is that when we have some sort of try, let's say we have the word like hell, oh, then we also will have kind of this like character at the end that signifies, hey, this is the end of a string. So that if there was another word, maybe like hello friend, then friend would kind of come off here. But this is still designated as a leaf node, right, for hello. So with that in mind, what I want to do first is I want to first actually tackle the second part, just because we've been talking about like this leaf nodes, we've been talking about like the special thing. So we'll show where it's kind of relevant to this problem. So one thing to kind of notice is that this is actually true. And the reason this is true is that every string in a try is a leaf node, or creates a leaf node actually, right? So let me just write that down. Every string in a try creates a leaf node. And the reason is that every time we put like a new string in a try, we're going to have this like square signify, hey, this is a leaf node. So with that in mind, one thing to kind of notice is that that's not necessarily the case in a binary search tree, right? So if you have two elements in a binary search tree, one of them is going to be the root and one of them isn't going to be the root, right? So this element that is the root will never be a leaf node in the future. So there will always be fewer strings than leaf nodes in a binary search tree, right? So yeah, that's why this one is true. So now let's kind of go back to the first one. So the height of a try is bounded by the length of its longest key, and this is also true, right? So when you have some sort of try, then the length of the longest key kind of signifies how big that try is, right? The height of the tree, right? So like in a try might have the word like hello. So if a try has the word hello, and that's like the longest word, then you can kind of think that the height of this tree is going to be, height of this try is going to be 5, right? So let's move on to this next one here. This next part states the number of comparisons required to find a string, whether a string S is O log n in the worst case. So that isn't true. It's actually O of n in the worst case, because if you have some string S and you're trying to figure out if it's a suffix of a string, well, you have no idea where to look in the binary search tree, right? So if you're caring about the suffix, a binary search tree is sorted by the prefix, right? Oh, it's kind of sorted by like the start of the word. So if you're trying to find something in the end of the word, the binary search tree is going to have no idea, or it's going to give you no insight of a faster way than just searching through the whole tree, right? Maybe one example of that is like, let's say you have this tree and you have like the word pear. Let's say you have the word bear, right? Kind of notice here that these two words have like the same suffix, but they can appear in like completely different places in this tree, right? Let me just make this like actually reasonable. Let's say bear is here, pear is here, and let's say this is like here, right? So kind of notice like all these words have the same suffix, but like they appear in different places in the tree. So a suffix can appear anywhere in a binary search tree, so you'll have to look for every node in the binary search tree to know whether or not a suffix S is contained in the worst case. Okay. Finally, if a try has a height of greater than 3, the addition of a key can double its height. So this is true, right? We know that the height of a try is bounded by the length of its longest key, and the addition of a key could be double the height of the previous longest key, right? Maybe we have some try with the word high, and then I insert the word highway, right? Now I just doubled the height of the tree, did more than doubling, in fact. So yeah, that is all for problem 5. Thanks for watching. Actually, is it all? That it is. All right, I'll catch y'all on the next one.